Hey, it's Mr. K, Physics 30, Unit B, Part 2, numeric response 4 and 5 is what we're looking at. Cyclotron. Bunch of information, bunch of numbers, beautiful picture. Here we go. So the most important part here is to recognize that there is a separation and that separation has an electric potential difference. Now, basically, I want to do this question just like any other circle, where FC equals FM, and then I solve. The problem is that I don't know the velocity. Now, I know the velocity, I know the velocity going in as it approaches the D separation, but I need to know it after it leaves that separation, having just accelerated, gaining energy. Now it has a new velocity. So really there's two steps that I have to do here, and it looks like this. So yeah, I gave you a whole separate page so you could do it, and here's how it looks. First, we think about the change in energy in the plate. So Q delta V, we gain this much energy. Now I had to find my initial kinetic energy, add that change in energy, and found my final. Once I found my final energy, I could figure out my velocity. Now this is important. Now that I know the velocity as I leave the separation, I can now start to treat this as a uniform circular motion problem and then solve for the radius. So if you recall, for uniform circular motion, Fc is our new F net. The only force acting is the magnetic force. mv squared over r equals qvb. We manipulate and we find our radius. So when I enter that thing in, it's going to be 8072. And then for the principles, basically it's one of two options here that I went for. I went for 5 and 2. 5 being conservation of energy, talking about the acceleration in the plates. And then 2, uniform circular motion. Another option would have been 3 and 2. So the work energy theorem could also be used to talk about the change in speed or the acceleration, but then you have to come back to UCM, uniform circular motion, to talk about that acceleration in the toward the center. All right, thanks a lot for tuning in.